Hello and welcome back to Lambretta-Lutz. Today I make a head design special. I decided so to show you how easily you can calculate the volume of your head and consumption chamber, and also then how to calculate the possible compression ratio and how to make it equal. So another interesting thing, maybe you can see it if I make it closer up. No, so you see here the differences when I put it off. Here I put the silicone very fresh, didn't let it dry too much, and put it on, and you see how the grooves are making like an O-ring. Yeah, so two O-rings, and that is the reason why this, after making this modification with the head, they are completely sealed. Here I did wait a little bit too long, so the silicone was already too too dry, and you still have here some liquid O-ring, but it was not really touched. So you have to clean the surface very good. The leak down test was okay, but just to show you some differences on that. So I will now change the scene and show you how to first calculate the volume. So how you calculate the volume and how you do it the easy way. Yeah, there are probably many ways. My way is like this, and I do it since many years, and it is working very well. What you need is you need the piston that you need some water, you need the head for sure, and you need a scale in a kitchen, possible with at least one digit after the commutator. So what are the things to do? And you see already here the result that I have very different chambers. Yeah. So the first thing that you are doing is you're putting your head on a scale and put it to 0. So then the second thing is, now where I know how much volume it is, you putting water into the chamber. And as we know that we here have approximately 18, I will put 18.5. So I filled up the center. So I have 80 now, you see it here. So that should be, according to this, completely okay. So now we actually make a control of my first measurement. So the next thing is you put it on and you see some water is dropping out. So not doing too much, then the water will go into scale and maybe destroy it. So you have to have a good feeling already when you do it the first time, maybe put some protection over the scale. So, and now we are taking this number and write it down. Write it down. I had a pen before. Interesting. Okay. So we have 256.4 grams. So that is what we measure now. Now we're putting away carefully the piston so that it is dry, and this water we pour back. Okay, good. So now we go back to 0 and taking the weight of the piston. That is 238.3. So, and then we easily can calculate how much is the difference. So we have here the numbers of 256.4 minus 2038.3 is 18.1. 18.1 grams. And my first measuring are interesting. So we have actually now already a difference of 0.3. So that means my first measurement have been this. So we take it. So that was a second. The first one was 2573, and the weight of the piston was 238.4. That resulted in wrong. I took the other calculation, so I have to take this. Okay, once again. So the first one was 256.2 and 238.4 grams equals. So, and that was a 17.8. So we have here a delta of 0.3. So you can see, and that is the reason why you're doing this at least 3 times, to have clear that you make not a mistake and that you're measuring. Then you can make a average on it. After 3 it will be okay, because there will be later much more influences on other things, but on this we are accurate. And I tell you already, that is too much. I will calculate later with my program what we are going to do. So either we leave them as they are, or so I have now 16.9. That is too less, so we need at least 18. 18. Okay, that is good. So everything dry and clean. Okay, and the third one. Okay, carefully putting the water away. There's nothing. Okay, great. Correct the position again. So, and putting it away. So, okay, we have now the third one, 256.0. So again, a little bit less. Interesting. So we have again and again less. I will just give it a few more drops to not see if by putting it away. So that will be okay. Now we got a good result. So suck it away. Okay, good. There is nothing. Excellent. We see it's 56.2 again. So it's like the first one. So pouring the water away again. So let it drop up. Put it to 0. And we have 238.4 again. So means that in the second measuring I had a little mistake. So again, so we have 256.2 minus 238.4. It's 70.8, like the first one. So we're now making a average. So we have this plus 70.8 plus the 18.1 is 53.7 divided by 3. So we have here 70.9 grams. That means milliliters. So I will, with that, correct it 70.5. So the same procedure with the other one. So we had to make it similar, I take also the spark plug that was in the other one to have no influences from the spark plug. Actually, what would be better is to take the 2 spark plugs that you are using, but these tolerances are, I would say, okay. I can accept it. But there are types of there's different types of spark plugs where you can have a variance of already 1 milliliter that has an effect of the compression. So you can actually tune your compression by just changing a spark plug, just by the way. So I will go to 0. Build the average as well, because we have 2 close and 1 not close, plus, and you know the result, 55 to, so it's 18.4. 18.4 grams in average, and in average 19. So versus 70.9 grams average. So I will correct here this data of 0.4. So with these two numbers, I will now go to the calculation program, and we'll see what this is telling me. And as we here have heads that have a step for the centralization, make it centric, is 124. So we have approximal 120. So that means with a 0.5, we have just a 0.5 side squish. So that with this kind of volume of just 70.99 will be a compression that this engine will be destroyed in no way. So there we have to do something. So another important thing that needs to be measured is the deck height. So and here I have to clean up the surface for the measuring. So I will just do it on one point, and it's 1.8. Okay. Okay, it's 1.77. So that we need for the calculation program as well. What kind of programs I'm working to get the right calculation for the side squish, and what the heads actually have for a design. So here you can see I put the information in regarding the engine that I have with the bore, piston, connection rod, and expected peak power. The compression for me is always effective, not the geometry, so it's called trapped compression radio here also. And here you see I put the calculation of one of the head into it, that actually then with a deck that is here wrong, I have to correct it. We had 177. Yep, so it calculated here in 2.8 and take it over here. So on the other side, we have with the stack, and as the head has a gap and going inside the barrel for the centration, it has just a 0.57 side squish gap. That is far too low, and you see exactly here on this graph what is happening. So the side velocity is much too high, and the cold velocity is already 20 too high to the recommended. So the detonation risk is much too high even on hot. So, and here you see if you would put the head like this and start the engine, you will just go a few meters, and yeah, okay, this is side which is clear. So we don't want to change anything on this head. So we want to keep it as it is, even with this with this small consumption chamber. So for instance, we have standard sizes of gaskets. So we have, let's take a 1 millimeter gasket. So with a 1 millimeter gasket, we have a kind high side squish gap then from almost 1.6, but you can immediately see. So we come here with all the data. So the side squish volume is already good. The velocity is still a little bit higher, but it's okay. And so the side squish ratio is good as well. So, and with that, the detonation ratio goes is even on a minus 55%. So bulletproof. So I would not go for any change then with this head. And as the engine is the same, but the heads are different. So I go now with the other calculation here, 18.4 we had here. So, and we look, yeah, good. We have a little bit too low side squish volume. That is sometimes not to understand why is it so, but it has the formulas in between, and it has to do something with the recondimated PSA that you need for the side squish and area and from the code velocity area. But with that, I will go not too much into details. So we know we need a 1 millimeter gasket. With that, we are good to go to use this head. And the good thing is the small gap is 1.2, so we have even 2/10 of a millimeter for that the consumption is centralized, and that is good. So we will do this, and with that we have a good situation. So far for my calculation regarding the head design. So checking after the check on the situation regarding that we need proximal with this head, a 1 millimeter of gasket to have accordingly to the cylinder height to the exhaust port. We now have to see what variants we have in the timings itself, because we know there are differences from the heights. And well, everything is easy when you just do it with for one barrel, but it comes to two barrels. You have to synchronize this as well. So I prepared this already in a way. I cleaned up the surfaces. They are done with this gasket kits that has been already compressed. So, and I have here a digital device for measuring the angle, very useful in many cases for timing points and so on and so forth. So I take a feeler guide, a very small one, to have always the same situation. So as soon as this is touching, I put it to 0 and get 1. So I guess it's something around 180. You can see it already, because if you put it both exhausts at the same height, so both are barely open, so it seems to be that they are exactly 180 degrees. So I leave it like this. I said 180. So we have 180. Yeah, it says 0.1, but I probably believe it should be 180. So the next thing that we should consider is we're measuring the downblow timing, and then we calculate it. So to have a double check. So the download timing is very low, and as expected, this should be 27. 27 measured. So, and now we get to the timing point again. We'll put it up. Okay. Okay, now. So 20.6, 127.6. So that should not be okay. So that is measured here. Then we change it and we do the same stuff here. First the exhaust. I mean, should not be surprising. Should be something around 180. Yeah, 186. So that is 180.6. A little bit down. But let's see how much it variates now. Okay. Also here, 27.4. And That's surprising. $25.6. 125.6. Okay, that will be explaining something. So we're now making after this. Okay, so here I have to check the measuring again, because that is more than 2/10 and seems to be not accurate. And now we have the deck height to calculate as well. So I will do it in an up and lower position. Just turning, hold it parallel. So at the exhaust we have, no, that cannot be, oh yeah, that's not on 0. So again, okay, 166, 127, yeah, that makes sense, because I measured without pressing, I measured 177, so we have now just 167, yeah, makes sense, and here you can see how much paper actually gets compressed. That is the reason on very high performance engine, where you have the smallest side switch you can go with paper under the cylinder. It has to be solid. And here, okay, that is okay. We have here 162. So that is a tolerance that I would keep to a normal. So now we do it the same here. Oh, okay. Wow, 227. Okay, my filling guide sets 300s, and now we have a variance of 6. Wow, that are really tolerances differences. Okay, let's check here. And 213. So that I will check again. That there was nothing in between. Cleaning up here. Because that seems to be a lot. Unexpected lot. No. 25. And hi. So that is now interesting, and having this measuring, so I will write now all the data that I did measure, so that you can see what for kind of situation we have here. We have an exhaust measured 180.1, so 180. We had the transfer ports of 127.6, so makes approximal 26.25 for the blowdown. So then we have at the spark plug side here 2.15 and here 2.25. Okay. And now the head to this has at the exhaust 1, 2, 4 and here 1, 3, 7. Okay, so that is the situation here. Oh, that is the situation here. Now I put it back before it fell down. So now the other situation on this barrel. I did measure 180.6. I had transfer ports from 125.6 that I do not understand why that should be 2 degrees difference. And with that, we would have blowdown timings from 27.5. That is 1 over 1 more. So then we have at the exhaust 167 and here 1 1.62. While for the head, we measure at the exhaust 142 and 125 here. So, yeah. What we have so far, we have a variance in steering times that from the exhaust timing is not so different, from the blowdown and from the ports quite huge. That is, from my perspective, very strange. So I have to measure the heights of the port height to the top of the barrel. So that is one case. We measured before with a feeling guide that we have about 2/10 of differences on the fusing housing to the original case. While when we now measure, it is 6. So this is deck height is 2.2, while this is just 1.6. So, and now on top, here we have 1.3 to 1.24. So we have a variance in the up and down one, while here is the same from even 2/10. Okay. So I would say with this funny notes, I will go back to my calculator and make my mind up what is the best of to do to bring this as equal as possible. Now you maybe would say, oh my goodness, but take it very from another case. Yeah, this deck height, it's not okay. If I would have compensated that what I said before, I would go here 2/10 lower. Then we still had a variance of 4/10, what is very surprisingly. So it seems so that both barrels have either a different height or something else is different. I don't know. I have to measure the bottom gaskets as well. So if you would now work normally, you would work with gaskets, head gaskets, and try to get the side squish on, like I calculated, 1.6, 1.5. Then you probably would go here with this distance. Let me see. Here with 2 to 5 and having 2.3, you have 0.9. So here is just the tenths that you actually have to consider. Okay, so here. So as we have so many data, I was making my mind up how I can structure now to synchronize this data and to give you it visible for you. So therefore I make this kind of sheet. And I was looking for port time calculator that for free in the internet, and I found this Vespa Moto. The advantage of this, I saw that you can calculate the compression ratio in the effective way and in a normal way. So therefore, that is the advantage. So coming back to all this, what we did measure now. So actually, here are the data that I told you that I measured with the decks of from the head and from the exhaust side and from the plug side, and what makes a delta. So, and the head volume, all this I show you in the video, and here you can see it very visible. So I did it for the right hand and I did it for the left hand. And I put this data into this port calculator and also the volume of the cylinder head. So in fact, you see that my measuring could not be correct because the top edge of the both cylinders have been equal, and therefore this has to be in different case. So I probably did something wrong with measurement, but it's good. Yeah, so to see and have a double control. So we from the calculation, I should have had something of 177,
and 126. That actually makes no sense. So here you can see that there was a big mistake, while here on the side um, from the calculated and from the measured, I'm not so far away. So the other thing is this many numbers of different kind of deck heights and even invariances and what it then actually makes for a side squish. And you see that currently on the right hand, we have a side squish from only 0.3 left, while on the other side is 0.9. So it really needs a synchronization so that we both have that we coming in a good situation. So the first thing when I'm looking here, having here 1.67, so almost 7, and here it shows me that there is a different not of 0.3 millimeters as shown in the other part with a glass plate. It should be almost 0.5. So I try now. My idea behind is now that we have really equal numbers on both sides. So I would like to see to have this a little bit up so that we here maybe reach 0.6 and this coming down. So then that with 0.6 in average, we could play around just having 1 millimeter head gasket. And we will have from the other calculations seeing the 1.6 side screws. So therefore, I will start to changing these numbers here and saying, okay, I want to go up here on a little bit. So 0.7, 0.8 maybe. 0.0. I have to make it with a point. This calculation is just working with points. 8. Okay, so we have 178, 100. Okay, yeah, that sounds good. So, and I will go down here. Then as well to bring it to 1.8 as well. So it means three lower. 1.8. So we have, sure, and that has to be equal the steering point. So the change here would be 1.3, and I know I used Indian gaskets that have 0.7. So maybe in the kit it would be good to have a 0.8 cylinder bottom gasket. So, and so that would be my change. Okay, so, and then on the other side, I go here 0.3 down. When I have currently the Indian gasket that has 0.7, then we are at 0.5. So we have to go maybe in two steps. So 0.5, and then trying later 0.3. So and then we have this 50%. So what would it mean? So we can, I would now correct here the data just from the side scripts, not from the timing, because the timings we have changed here already. They are not synchronized. That are web calculations. You can take it for free. And here's this grid I just built. You can make it on paper. I just built it to have it more easy and visible for you and me as well. So we will change. We will change to 1.8 here. That is interesting. 1.67 once before. Then maybe there's a mistake in the calculation. It should become it's the average. It's the average. But it's true. Yeah. So here it's 40. So that means in the end, I still have to work on the. In the end, we with 1 millimeter gasket, I just will come to 1.4. Okay. So that means definitely if I have to work on this head. And here on this side, it will be, then we're going down to, here, I miss it. Okay. Now we see. So we could come closer. So it's 1 point, okay, good. Yeah, goes in the right direction. So, and see here as well. So we go 1.8 here down because, and 1.8 here down. So we have 0.5. So we come to the equal point. And then with 1 millimeter, we are going to 1.5 millimeters of side squish. So Well, and then we put a little bit of silicone that has something as well. So I would go for this. So I will go downstairs now in the workshop and proceed. And then we can see if with maybe 1.8 of deck, doing that with 0.8 and with 0.5 or 0.3 on the left hand, if we are then coming to the result. Okay, see you downstairs again.
So the calculations show that there is something not like it should be. So maybe the tolerances are, from both cases, bigger than expected, and somehow we have to find a balance of making now too much machinery that you either cannot proceed at your home. And so I was making my mind up what we can do. And the advantage of the monster kits are you have at least 3 different size of gaskets, and with this bottom gaskets from the barrel, you can do a lot. So there is 108, 105, and one with 03. So you have a good variances, and you can double check. So, and by not bothering you now about this action, I can now show you, because I think everybody knows how to change a gasket from the bottom and then making the measuring as a sure. So you see, I'm putting these numbers away, and I will give you the new numbers. So the new numbers now are, and I wrote it down. So for the right hand, we have now the situation with 0.8 bottom gasket. We have here on the exhaust side 1.77. That is now not fortunate to show there. And here's 173. So it's a better set. And from the timings, I measure 125.3 from the porting and 178.3. So obviously my measuring was not correct, and the calculation of the porting showed them as well. So then on the other side, I first try it with 0.5, and that didn't work out. So we went down to 1.9, and to the duration timing, I was then not even counting, because I said, okay, now I want to have now a deck height that is as equal as possible, just with changing the gaskets. So I changed this one down to 0.3. So now it means this both are 0.5 in differences. Sounds a lot, but it gives also advantage. I will tell you why. So, but coming now first to the points. So we have here now 1.79, and we have here now 1.72. So we are in the sevens. And from the timing, measured, not calculated, measured, was 178.4. So, and 124.9. So everybody who was measuring already timings for sure will know, okay, this is a very accurate, because we have 178 to 125 on both sides and everything. So we can now say the barrels are very equal. So, and it's good. It is really good, because we know we have at now exactly 0.5 differences. So that would even give us a possibility to go here on a 0.5 metal, so aluminium spacer, and on the other side 1 millimeter. And I prefer, honestly speaking, aluminium on the bottom more, because then the cylinder cannot set and the side squish cannot change. So we actually now make a setup for this variance in a, I would say, very practical way, because all what we used is not a big machinery. We all used just the gaskets in the kit. So, but now when we calculate it, we still have the situation that now this is 1.7, that is just 0.1 of the side squeeze that we need. And here is the same. So we said with the calculation, I said we need 1.6. So putting now the heads on it with this different heights that they have with the central step, we have around 0.3 to 0.5, so there is a little variance in the heads of 0.2. We are not talking about high performance energy, so therefore it will come in natural ways. Both cylinders are producing 25 horsepower. We will end up at 48, maybe 45, even maybe 50. So, and with a lot of torque. So we want not to go in a direction 70 horsepower and plus, because then everything has to be super accurate. So what I'm thinking now is, the best way is what I put now is I have here two, oh, that is 1.5. I thought they are one. So I have to find in my bunch of head gaskets, two with 1 millimeter, or at least one with 1 millimeter, to then see how we manage to have the right side squish. And well, then we again manage it in easy steps to bring everything very unequal. So lucky-wise, I found two old gaskets, head gaskets, to at least see if with 1 millimeter we come then with a side squish on that what we are looking to find. I will put some, do I have it? 1.5. Solid, yes, it's, and I have 2 millimeters as well. Okay, excellent, good. Use this side to get the solder through. We have already that point, so it gets very easy. Good, let's see what we have now. So 1.88, and here we had 1.63. Okay, so we have to do something on the head. The interesting thing is, where is less? Here's less, here's high. Ah, yeah, it's right. So here, so I have to get it a little bit and making here a little bit more off so that I can go down, and then we can go on both sides. So, okay, I know what I have to do. So minus 0.2. So I have to adjust it here to, minus 0.2. Okay, and now the other side. Well, 1.42, and 1.43, at least equal. So means on this head, the small variance is okay, but we have to grid down, and that will bring the same approximal chance to reshape the chamber a little bit and bring them. So we have to bring that down 0.2 as well. But all over. So that would be the case. That would be the case if we would use the paper button seals and having then everything as it is. I think the timings are super equal. We managed to have almost as calculated side squish. So we will not finish today, but we have a conclusion what to do. And I probably will make tomorrow an order and we'll get aluminium spacers so that we have a solid distance that is not changing by paper leak or whatever. So I'm prefer to work with aluminium spacers on the button, and we will have 1 millimeters of spacers in the top. And then I will show you something important. The out view is how to use this ones then for having the chamber and the head centralized to the bore. As you can see here, the heads are always coming already with the 10 millimeters, but this one's not. So, and if I now going to use a 1 millimeter, this little step is too little to make a centralization. So, therefore, we will have now the advantage that we have already here this circle. So, before I will work with this, new gasket, I will pull off all the barrels. I will fix them with 3 studs, and I will drill through the heads the first hole. So, I see it's not in. Maybe it's better to explain. So, now you see, if you can see. So, the chamber is very good central. So the chamber is very good central, and if we would use a step, it would be an easy way. But if you're now looking for the drills in the holes, you see already the head is not equal. So means you have to fix in the position the head and the barrel so that it is fitting here also and is not turned. Then you need 3 studs you can take from the old one. You fix them together, and through the head that has already 10 millimeters, you get guided to have the drill below. And so I go step by step, never twice, never 2 at the same time. So I really take the time to do step by step. And then you have the advantage that you can use this ones, and is very centralized to the then bigger hole that you will drill here. Because if you drill this holes first, how you want to centralize, you cannot go backwards. Then you have to drill all the way through, but that makes no sense. So you just put them a few millimeters, and then you see even the gasket will get an extra hold on it. So yeah, it is more effort again, but it's a good solution as well. So I will wrap up. We've started with the barrels as they have been fixed, and recognize that the porting times have been very different. The heights have been very different, even more than we had it when we had the when I put in the other part this glass plate and with a filling guide. You can see there is not proper accuracy. And it's still this way. We don't want to put it in a workshop. It should be still do-it-yourself built twin kit. So therefore now with the things that we had, and it's important to make you the numbers visible, take your time, write them down, making cross calculations. There are variances. It cannot be equal. You have cases that maybe are 30 years old and the new ones. So it will always be like this. So, and then it depends on, do you want to have a very accurate high performance where you will need a side squish that is on a 0.05 region, okay? Or do you want to have a Tourer running with a side squish of 1.6, then 1.65 or 1.62 doesn't play around. Yeah. So therefore, we use the normal paper to figure out. If it would just a plug and play engine, I would be already good for this. I would adjust it maybe with 0.1 millimeter spacer and 0.5 spacer, or make here variants so that I have the 0.6 at the other at this barrel as well. And the small differences on the timing that I would then have. Okay, yeah, okay. So don't break your head on that. Have a little bit trust of that this engine will run anyway, in a good way and in a way you never expected before. But that was now an important step, and I hope it helped you a lot in your build. So thank you for watching. Please leave a like. Please comment. I'm always happy for the comments and try to answer them in the next time or directly in the comments. And sure, subscribe. I see you really like it. I have a gain of subscription, so thank you for this. And so we're stepping forward, step by step. Thank you. Have a good one.